Hi and welcome back to MDriven. I've been watching this interview done by the pragmatic engineer on this channel here with Grady Booch, which is the co-creator of UML. And I made some reflections, and I will just highlight the interesting parts, the parts which I think are interesting. And of course, you should go and watch the whole thing for yourself and see if you agree with my editing here. So, passing the intro, I'm skipping to minute 6 and I'm going to listen a bit what he says here.
The IRS system written in IBM 360 assembly language, running on emulators upon emulators upon emulators. But that creates really difficult problems because some of that code embodies business rules that are within the assembly language itself. So how do you change that? And the answer is you're faced with a real human problem of how do I transmorgify old code in COBOL assembly language so that it can work on modern technology. There's only so much you can do via emulation. And then when you consider that the government, makes new business rules every year, how do you keep up with that? That's a real...
So, two things. It's a bad idea to put business rules in low-level code. We know that. Most of the software engineers don't have an option. They need to put it in code because code is their tool. So, and that's a bad place to have rules, because rules are part of a structure. It's part of a common shared truth. And then it shouldn't be hidden away somewhere on a server somewhere. It should be documented and open. And if it's documented and open, why can't we use that document to enforce the rule? Why do we need to code it? So that's the main, I think, challenge for us going forward into more and more complexity when it comes to information. The second thing that I think is important is that business rules change. As he alluded to, that he said that the government changes the rules every other year or every year. And of course, other types of businesses changes their rules even more often and invent new rules and remove old rules. So everything is about catching the business rules, and that will build up what the information system content is. And what the content is actually what's the challenge.
The James Webb Space Telescope currently uses the UML in its design. That's pretty freaking cool if you think.
Yeah, that's cool. One thing that he says that I found spot on compared to my experience.
Basically saying, hey, here's a new way of thinking about the world. And so it said, look not at algorithms, but look at combining data and processes, algorithms together in one thing, thereby classes. Now, we did some things right. We did some things wrong. I think the things we did right was classes make a lot of sense in terms of abstraction. What we did wrong is we overemphasized the notion of inheritance. Inheritance was all about let's, save code because we can, build generalizations and the like. That proved to not make a lot of sense because we ended up doing lots of disparate kinds of abstractions. That's okay. Fast forward to today and people say, well, what difference does it make? And the answer is it's part of the very atmosphere in which you breathe. And so you don't even think about it. You look at...
Yeah. So everything today, when we talk about information in information systems, assumes object orientation, classes and associations between objects of those classes. It might not be obvious to everyone how much they rely on the legacy that Grady Booch has provided us with. Here is a section where he points out that there has always been criticism to overuse the computer. Let's listen on what he says.
It wasn't like that back then, right? So could you talk us through what the environment, the technology was like? So that what made the Booch method so new, interesting, or innovative?
Well, let me go even further back to the 1950s and show you a parallel story. There was a time in the growth of algorithmic programming languages where the idea of a subroutine was considered controversial. Why? Because doing a function call added at least 2 or 3 more instructions, which was computationally expensive. So even function calls and decomposing something into subroutines was viewed as an architectural aberration.
So Grady Booch worked at Rational Software that created the software tool Rational Rows, which basically was a UML modeling tool to draw UML diagrams in. And let's hear what he says about that.
I think that was a hit.
Yep. So rational software, the ROS, Rational Object-Oriented Software Engineering, was a personal productivity tool, if you will, that ran on an IBM PC. It also ran on, I think we eventually moved it to a number of other devices. It ran under Windows in the first one, that basically allowed you to, draw UML diagrams, not UML, but Booch diagrams, so that you could then reason about and think about your design. We did a little bit of code generation, but really it was just a design tool to help organizations think about their designs. And people use it quite well to document and specify and build their systems. Now, we started making lots of money off of it, and so we started acquiring companies. We bought a requirements company. Ed Jordan came to me and said, go look at these folks. We did. We bought a small company out of Cambridge called Pure Atria, which was led by a gentleman by the name of Reed Hastings. Reed came to us and we bought his company, and he said,
and we're talking about the founder of Netflix, right?
Yes. So we bought his
Small
company.
World.
Yeah. Reed realized he's a lousy CEO.
Yeah. So Rational Rows as a modeling tool is similar to what it did with what MDriven Designer is today. The added value of MDriven Designer is that there's a play button, and also the added value in the whole ecosystem of MDriven is that this play button also can be enterprise grade by sending your model to an MDriven server and some MDriven turnkey front ends to get everything going completely model driven. And then he comes in and touches upon the need to look at a system from very different perspectives. And I'm going to listen and then...
He hints at with the Booch method, and that is looking at the world through multiple points of view. Philippe has this idea of the 4+1 view model, which he grew from his work with building the Canadian...
So here he mentions the view model. It doesn't exactly mean the same thing exactly as we do when we say declarative view model. He sort of uses it as the documentation artifacts that are needed to understand an information system. And of course, view models are part of that. Now the interviewers poses a question about if he has understood things correctly. And this is an interesting part.
With UML, we have the different boxes of different classes. We have the arrows between them. They describe relationships depending on the type of the arrow is, and when you look at this whole diagram, you get a sense of the structure of the software you're building.
Yes. So if you look at the very first line of the UML 1.0 standard, I believe it says something to the effect, the UML is a visual language intended to reason about, visualize, specify, and document the artifacts of a software-intensive system. It says nothing about it being a programming language. In fact, I voraciously pushed back against that.
So that's interesting. So Grady Booch does not think that the result of the UML model should be used beyond just the thinking about system. And I think that he has come to this conclusion because what he talks about with software architecture, at least I get that feeling listening to him between the lines, is that he talks about the components that build up the system, not so much the information within the system. In MDriven, we focus 100% on the matter within the system, information. And that are classes and associations and attributes and view models to build up the complete information structure of the problem that you want to solve. And you can't really solve anything if you're not allowed to play with it. And of course, you can play with it with diagrams alone, compile it in your head and start to think. But it's slower than having a computer just turn it into a running system so that you can actually give it to users and get feedback instantly. So it's interesting to see that he has this take on it. I have a totally different take, but I think that the different takes comes from him being a more infrastructural person when it comes to software engineering. Which kind of queue should I use? What kind of database should I have? Which cloud service provider should I use? But I am strictly into what's in the system. What kind of information is there? What are the business rules for that information? What happens if this is deleted, etc., etc.
It was a language meant to think about and reason about a system, to think about the world in object-oriented ways, particularly in ways that you looked at it through multiple points of view.
So, I totally agree. Think about the world and look at it through multiple points of view, especially when it comes to the information handling, and then you have the different use cases of the declarative view models, so the different perspectives for the different roles of the different users. Let's hear what it says.
DevOps today, by the way, is simply an amalgamation of deployment and implementation views. But we didn't call it back that way then. We looked at it from those kinds of views. And that's really where UML 1.0 was. It was meant to be, how do I think about these things? How do I reason about them?
Yeah, so what he says there, that he equates DevOps with certain views in UML, is further makes me even more certain that he talks about software architecture as principles on how to do things, what kind of infrastructure components to use and how to connect them together, and not so much, maybe not at all, about the content of the information system. And this is actually interesting because it seems that this is a very common view. So it's not that he's the strange one, I'm the strange one. I totally accept that, but still, being strange as me gives enormous advantages sometimes.
And I always intended for, you'd write a UML diagram and you'd throw most of them away.
Yes, absolutely. You do a lot of diagrams because you're working on a specific perspective of the complexity of the information within a system. And that get messy after time, and you can have how many diagrams you want, and you can throw away the diagrams. But the model the classes that were in the diagram still survive in the model. So each the diagram is just a substrate on where you put classes that you have defined. When you throw away a diagram, you don't really throw away the classes on the diagram. It's just the placed classes on the diagram you throw away. So I totally agree that don't spare on the diagrams and do many different perspectives, anything to actually help you think about what's going to happen. But also, when you have a play button, as you do in MDriven, you don't need to think too hard. You can just press play. It's a 1 second job, and then you get a lot more context and information than you do by thinking really, really hard.
Now, unfortunately, many people didn't do that. And in the move from UML 1.0 to 2.0, there was a faction of individuals and companies who said, no, we want to make the UML very precise. We want to turn it into a programming language. And that was, I think, a profound mistake. I never intended the UML to be a programming language, but...
So there he says it. It shouldn't be a programming language. And why has he reached this conclusion? Well, if you are part of my side, where you think about that the UML model describes the content within the application, then it's fairly uncontroversial to say that, well, the content of the application, of course, must be in the application. So why can't the model be the application? But as he isn't really at that level, he is at the level, what protocols should we have between these three system parts, so that they authenticate correctly, and what happens when communication fails between these three system parts? How many retries should we have? Those kind of questions. And then I totally agree, that's not a good fit for CodeGen, and that's not that will not work, I believe. But it's important to distinguish that he's at another perspective of what he uses UML for. We are both using it for visualizing and thinking of abstract things, and he thinks of complex information systems infrastructure, as I like to call it, or how the system components are interconnected. And I think about what's inside such a system. So if you want, you could think of it as he's talking about the how should we do this system, and I'm talking about what is the system. So and the UML is a great tool for describing any kind of human thought and structured thought. So it's good for anything of that sort. And what we have sort of taken and made the most of, we think, and we will continue to make the most of it, is to actually fix the problematic inside of software. So here's a section where the interviewer just reflects that no one uses UML in real life. Let's hear what he says.
Wow, what a story. So I studied UML in college, and to this date, it's part of several college curriculums. But interesting enough, in the industry, I've just not really seen it used for anything, at least the companies that I worked at and the startups and scale-ups and large companies I work with. I kind of see a resistance to using it when it's brought up, claiming that it's too formal?
So that's interesting. Too formal. Of course, if you're not going to use the result to anything, why should you produce the artifacts? The only reason for producing the artifacts is that you have good use of them. And if you were to focus your challenges to the inside of the software system, what this system actually should do, so you need to name all the classes to things that exist in your domain, so that you can express the business rules with the domain names. Then, of course, it's not formalism. It's just good requirement management to use the words that the domain, I use business or domain interchangeably. But it's interesting to hear that he thinks it's too formal.
Because we do use architecture, right? We use boxes and arrows and
that's also interesting. He uses boxes and arrows, but he doesn't use UML. And what he probably alludes to is that he uses the whiteboard to think aloud and to stand in group and think about something. And then they just wipe it and go and have coffee. And of course, that's good. It's better than nothing. But it's sort of a pity. And that that they can't get some little bit of more structure into their daily work.
We diagram. I'm curious to know, we talked about how UML was used by 20-30% of the industry at some point, but what happened in your view?
To, contemporary architecture, that I've got a shelf full of books on architecture, both in the older ones and new ones. And if you look at what a lot of people speak of as software architecture today, I think it's reasonable and sound, and there's good stuff there. But in many of the kinds of systems these architects talk about, the architectural decisions have largely been made for you. I'm going to build a system that requires message passing. Well, let's go find, Rabbit MQ or whatever, or Redis or whatever I need. The architectural decisions have been made for you.
So this is what he sees as software architecture, to make these decisions on what large coarse-grained components to build the system with. He didn't have coarse-grained components to use in his youth. They had to roll everything on their own. And a lot of work went into actually getting the structure of the system to work.
So a lot of the activities of contemporary architects is simply taking very large frameworks and components and weaving them together, which is a very noble and wonderful thing to do.
So this is where we totally disagree on what the hard thing of software architecture is. I think the content of the application is the hard thing, and both these guys think it's the infrastructure of the application which is the hard thing. Interesting.
They also represent systems like Meta and done as particular. They have grown their architecture and system over a few decades now, and the stuff they're building on top of it is largely evolving and building upon those APIs.
Here's a section where further points out that they are talking about coarse-grained components rather than the content of the information system.
So do I understand it correctly that you're saying that software architecture has changed from the 90s and 2000 when systems were new, architectures were new, software architecture was still a lot more novel. And if we look at venture-funded startups and big tech today, what we see is, one, they're just not as risky. If they fail, big deal. And then two is we can use a lot more software that's out there and been architected. And, we can, for example, use Redis as a cache.
So again, they come back to Redis, which is a cache software pre-built. When Grady was young and was learning how to build software, there was no Redis. So if he needed a cache mechanism, he had to roll his own from scratch. I totally understand that that was a challenge then. But he also was challenged with what the system actually should do. Caching is not an it's a non-functional requirement. What I mean by that is that it brings no value. I can go and say to the customer that that you needed to handle invoices and make sure to invoice all your 100 million clients just in time. And we're going to do XYZ of technical components down at the server farm to make this happen. And he says, well, I don't care, just make it happen. So, but if I were to say that, I don't really know what you mean by invoice. Wow. Then I'm thrown out, right? So the value for me as a software architect or information architect, which I think it's a better word, is to understand what the business problem is and put my focus on catching and designing the solution for that business problem.
And it is there, it works, we don't need to think too much about it. And then the third is that there's a lot of startups who just don't need ceremony. Basically, they don't need audits, they don't need formality, they can just go like, all right, let's just do it however we want to. We don't need that kind of auditability. Do I understand that these are the changes that are in play with software architecture? And is this why like some of these formal methods are just not as popular with startups and scale-ups?
Yes.
Okay. And I totally agree that who needs that kind of formalism for infrastructure of a software system today? No one. That's not the way you do it. You still would need that kind of formalism to manage the content within the system. Oh, I feel I repeat myself, but this is so painfully obvious that I have to, I think. Sorry.
In fact, I think it goes to the root of the economics of software development. Let's go back to the first age of software, first golden age. The machines were far more expensive than the humans. And so it required one to do some thinking before I even got to the machine, because machine time was very, very expensive for me. And so, yes, algorithmic decomposition, structured analysis, design techniques made a lot of sense because we needed that kind of optimization. If you move to contemporary times, computational resources are like water to a fish. They're
correct. We have all the compute we can wish for. Still, and the human resources are really expensive. Still, these guys don't think that we should move away from handwritten code to some higher abstraction, and that's actually the this is what I don't get. It's sort of inconsistent.
they're available to anybody. I've got on my desk behind me, I've got my own personal cloud of
Yeah.
4 NVIDIA single board computers, which has more processing power that existed in the world in the 1970s. And that's pretty amazing. That's a few $1,000s there. And so the economics have changed vastly such that you don't need to think about it so much because heck, it becomes disposable. AI, I think, is also changing that because it allows me to build things where I don't even have to think about design. Heck, I don't even have to think about software. I just prompt it for those things to build something and one-offs. And once I'm done, I throw it away. So in that sense, it comes back to the economics, but there will continue to remain a class of software that's new, unique, breaking new ground that still requires that kind of architectural thinking.
And it's interesting.
There it is. If there's something new that you're going to build, then you need to be structured and think and design. Correct. But what isn't new? Whoever went to a client project and discovered that they wanted the exact same thing as someone else. Maybe, well, I don't know, maybe people do that, but I never been in that situation. Things get unique really, really quick. That is what things do. If you want to win in business, you need to be unique. If you are like everyone else in business that you compete with, you, at the best, you can come in as tied. Most likely you're gonna lose. But you want to win. And how do you win? Well, you do things smarter. And how do you do things smarter? Well, you evolve constantly. You find small issues with what you do now and you optimize. Not optimize making them a few CPU cycles faster. Optimize, oh, we don't need to do this step if that information could be here already. That kind of optimization. And that's the driver for why businesses need their own custom-built information systems. But that won't happen if we put all the business rules deep down in code so that they are very expensive to change. They need to be very cheap to change. So we need to up in the model and maintain the model, and there should only be one artifact that you maintain for your business, and then you can start optimizing your business, and you can start to win as well. Oh, rant, sorry.
Because just recently I read how Amazon is using formal methods for AWS S3. They're publishing a blog post detailing like how they're doing it, and they're doing this to catch those really, really edge cases that only happen in 1 in a billion, 1 in a...
Yeah, so that's another thing with formalism, because classical software engineering, when you code and then you put testing on it, it's backwards, right? You do something and then you try to verify that it won't break. It's a very expensive and backwards way of defining and understanding a need. The way you should define and understand a need is declarative. You say what it is you want. And if you can express it in a way that has no alternative interpretations, then you're done. You don't have to do anything else. And you can try to break that with how many tests you want. There are no coding bugs in MDriven. There are think bugs. And what I mean by that is that things will do exactly as you declare them in the model all the time. That's not the case when you try to code requirements from an Excel sheet. You have like 1,000 requirements and you should translate them to code, and it won't always be an exact replica of the requirement, because the requirement, you can interpret that in 15 different ways, and also you can type this slightly strange code. So you need all that testing. But if you were declarative and you just express the requirement not in Excel but in MDriven, in UML, in OCL, object constraint language, from the start, then there is no to second guess you. That's the requirement. That's what has been tested and verified by the client. That's what's going to happen. And why would you want to second guess that? Just use it. Okay, so the think bug. What's the think bug? Well, that you thought this was a great requirement, but then you test it and you run it and you discover that this requirement sucks. This is not a valid requirement. So then it's a think bug, and that's totally different. We're gonna have those, loads of those, and that's why iterations must be so quick, because we need to root out all the think bugs. The problem with the traditional coding is that the think bugs aren't discovered until deployment, when the customer sees the things, because those are the ones that can judge that this requirement sucks.
System, then you want to use these services. In fact, here are some examples for it you can find on our website. So without them really acknowledging it, Amazon and Microsoft view architecture is still important, but there are enough patterns that one doesn't have to go through the process of rediscovering those, because I can build those things. And this is a representation of the maturation of our business.
So again, he alludes to coarse-grained components to build information systems. He doesn't talk anything about the content in the system.
We move from algorithms, which everyone can use, to design patterns, to now architectural patterns, which Amazon and Microsoft have codified themselves.
So that's where I think he makes a logical skip, because algorithms, okay, and then design patterns. So depending on the design patterns for what? Design patterns for infrastructure of the information system, or design patterns of how to manage information within the information system. But then architectural patterns are more like these cookbooks, that this is how you get an AVS service running in Docker with the Postgres database, etc., and how you connect them together. And all that is fine knowledge, but it doesn't have anything with the real business problem of information management that we actually, why we exist, why we bring value to business, is that we can understand information and put it in these cookbooks on AVS, so the information gets managed according to the rules that we have understood and declared fully, without alternate interpretations.
So let me switch over now to formal methods. Formal methods have always been a thing. However, formal methods, in my experience, have been a niche part of every software-intensive systems, because formal methods only go so far in what domains they can cover.
So now it's interesting. Now he brings up formalism, and it's true that it hasn't been very much used in software because no one had figured out how. But if someone had figured out how, it probably had been used, because we have lots of problems with software that would have been needed formalism. We have these examples with Toyota cars that the gas pedal hung and the car crashed. That was a software issue. We have the Boeing's MAX 8 planes that crashed. that was a software issue, etc. So if we had a bit more formalism, if we had an idea on how to put formalism into software, I think we should go for it. And I have an idea, and it's called MDriven. And Grady Booch, if you see this video, I love you, and I really hope that you can take some commentary on my commentary on why I think that formalism in software is actually always good.
And so you'll see, is what your example described, Microsoft began using formal methods in their drivers to validate the correctness of their things.
Their hardware driver.
With their hardware, exactly, yeah. And that was an important move forward. I've been with projects that use things like, I've got this system in which people might die. Let's run a formal analysis upon it. The thing is, though, that those formal methods don't deal with real world things because they don't deal with space and time. They deal.
So they don't deal with real things. They don't deal with space and time. Okay, point taken. Class diagrams in UML is very much a picture of this static image of information. This is what's possible. It's not at all an image of the dynamics of how that information is created and what comes first and what's need to be in place before we can do this. And that's the dynamics of software, and that's where time is of importance. But one part of the UML standard is that you can do state diagrams. And state diagrams is all about dynamics of how information change. So what we do in MDriven is that we fully utilize the state diagrams to keep track of the dynamics of the software system. So I don't agree, again, sorry, that the formalism doesn't work for that.
With functionality. So I have always found formal methods to be of use, but only for parts of a system and never as drivers of the architecture itself.
And I disagree. But that's because I talk about the internals of the system, the information within, and you talk about the overall coarse-grained pieces of the system.
Speaking of software architecture, these days the role software architect is not really popular anymore, at least at the likes of startups and big tech. Instead, we do have architects, but they're increasingly called staff engineer, principal engineer, distinguished engineer. The architecture is, and they do still do architecture, but there's a different focus on it. Now, you were there when software architecture was created, when the first software architects were created as a role. Can you tell us how you've seen this role be created and then evolved throughout the decades?
All architecture is design, but not all design is architecture. Architecture represents the set of significant design decisions that shape the form and function of a system, where significant is measured by cost of change.
Yeah. So that definition works both for his take on architecture, which probably is the world view of architecture, and my view of architecture, information architecture, the content of the system. Because the goal is to find a way to be able to, as cheaply as possible, do as much as possible with precision, and also don't build any technical debt from this, so that you borrow from the future and need to work harder later on. You should be done, and you should be clean, and you should have good practices and don't disturb others. So I agree on the definition.
So software architecture, an architect has this horrible emotional baggage around it. So think of it as it's all about making decisions. What are the decisions that shape my system?
So correct. It's all about making decisions, and decisions are made on different levels. It could be the should we use Postgre database, or should we use that wasn't a flat
an architect
Postgres database, or should we use MS SQL? That's a decision that is sort of influence what the system must do. But the most, it's non-functional from the business perspective. It's yeah, you're gonna skip
decisions and not just software kinds of decisions associated with it. So I think the role of the architect in effect has changed, because now I'm dealing with systemic problems, not just software problems themselves.
And have you heard about the role called solutions architect? I think it was created maybe 10 years ago.
Yeah.
And it's about people who are doing cloud architecture. It's fascinating. It's a role specific to the cloud. Right. And as you said, they make economic decisions.
Yeah.
So I wouldn't agree about that definition of solution architect. A solution architect alludes to the business value of what you have ordered. You have a need and you order something, and the result you get from that order is the solution, and that solution will need an architect, and voila, you have the solution architect. So that's just another word for the same thing, but it's again, I think the content of the application is the hard problem, and the business value problem, and all the other things is just other problems.
What services do I use? Do I use AWS, GCP? If I use AWS, do I use EC2, or do I use an?
Really, I don't care. Then hopefully your business client doesn't care either, because why would they? Of course, there can be the government, and some governments in the EU are afraid of storing backups in the US because of the regulation differences, and of course, so they might have an idea, but the idea is driven from totally different things than brand of cloud provider. I'm gonna listen a bit more, because they come into the discussion of what happens when things get old.
Systemic issue. You generally, if you're a startup, you're going to hire somebody who's done that before, who knows where the skeletons are buried, who knows, what the costs of these things are.
One thing what comes up with software architecture is migrations. I do notice that most large companies are being hurt by long-running migrations. And these migrations usually happen thanks to software architecture changing, for example, from going from monolith to microservices, or changing technologies, for example, going from Node to Go, or upgrading.
So again, they run into problems when they haven't dealt with the inner definition of the system. They just have this box that apparently is the system, and there is a lot of things within it, and it's built with coarse-grained components like a Redis cache and some other things, and that's the software architecture. And now all of a sudden they say that, well, we need to change version of the Redis cache and the MS SQL database, and it turns out they are not compatible with what is in the system. So now we need a migration. And of course, a migration of what? Well, a migration of all the code that describe the business rules within the system. Oh my God! So we need to know all the business rules within the code, and we need to know if they are affected by this migration, and if so, we need to change them. Wow. This is why we at MDriven, as I wrote in my book, as I wrote in the book, I'm gonna put a picture up here at the book. We do a clear separation of the inner definition of the system that we call the system gist. And that's the information content. And that's basically all the UML information, the definition, the declarative definition of what the system does. Having that separate from the substrate, which actually executes the model, makes it easier to change the substrate to a newer substrate that execute the model, but the model can stay the same. Why is this important? Well, the system gist, the information content, is much slower to evolve. It evolves all the time, but it survives as an entity for longer time. Like if you're a bank, you will have business in hundreds of years, and you will want your information system to go along. You don't really want, as a business owner, to rewrite every 3 or 5 years. There's no business value in a rewrite. There might be a business value in getting things to work, absolutely. But can there be other ways to get things to work over time than rewrites? And yes, MDriven can do that.
Major version of frameworks, for example, one version of Angular to the other one. How do you think software architecture and migrations are connected? And why do you think software migrations are just so darn hard and they don't seem to be going away?
They are. Migrations will plague us until the heat death of the cosmos, I believe, because
really
you're always building economically viable software, but then the technology is changing out from under you.
Correct. So that's why we at MDriven separate the system gist from the modernity, which actually executes the model. And then we can just modernize that every 3 years. And it's rather obvious. I just can't see why this isn't why everyone isn't talking like this. I don't know. You should check out MDriven.
That compels you to consider migrating. Consider the migration from monoliths from the 60s, 70s, 80s, till all of a sudden economically we had mini computers and now distributed systems. You're still not going to use an iPhone and put everything up in a mainframe, but those changes compel you to consider an architecture that better balances where the processing takes place. If all of a sudden I can begin to do edge inferencing on my devices, that's going to be something that's going to change architectures as well. So there are always these changes, both in the hardware as well as societal changes, if you will, that impact the structure of my systems, that are the forces that compel me to do this migration. But why is it hard? Well, another soundbite I'll give you is that the code is the truth, but the code is not the whole truth. There is so much that is outside of the code that represents design decisions, their rationale, why I chose this versus why I didn't choose that.
Correct. When you write code, you act in an environment where you get instructed on the overall concepts on where you want to end up, and you get requirements, and then you make millions of decisions, and that end up in the code, and the result is the code. And the code is checked in, and then it sits in a repository, and then you are tasked half a year later to look at the code, and you don't recognize it, and you don't know, is it me that did this? Okay, strange. That's just poor practice. As Grady alludes to here, the definition should really live together with as much contextual information as possible. And the model is such an environment. Why the model is much, much better than a prose document is that the model, the UML model, doesn't have any alternate interpretation. It's just exactly interpretable in one way. So that's crucial, because then you can always see that what the common truth was, and maybe the common truth has changed, and that's fine, and then you fix that. But so put in all the documentation and links to the decision material that you used at the time as well into the model.
Subtle things as to why did I name things this way, because of its impact that is long misunderstood. And so while the code may be the truth, the problem with moving migrations is that you lose, there's a loss of information.
Yes, so there's a loss of information when you code, and 1 year later when you're going to migrate to something else, that information is gone, and that makes it hard. So a model is a better vehicle for not losing information. I'm not saying it's perfect, but it's better. And how can I be so certain? Well, switching clients. I have several clients with totally different business problems, totally different models, and I can switch between these clients much easier when I have a model, because all the context really comes to me really, really quick. Watching the model rather than scanning through thousands lines of code. Yeah, and this was basically the interesting parts. Then Grady has some reflections on AI and large language models, which he sort of we can see what it says, or rather hear what it says.
And so rather than, software kinds of things, I've been studying things like cortical columns and the loops that exist in the hypothalamus. So I've been looking at architecture from the lens of a software architect into these kinds of organic systems. And so that now leads us finally back to your question, what do I think about large language models? The answer is they're pretty freaking cool. However, they are, by the very nature of their architecture, unreliable narrators. That's what I say politely. If I'm going to be impolite, I will say they allow us to build at global scale bullshit generators, because they are stochastic parrots. They do not reason. They do not
Stochastic parrots. That's a good one.
Understand, but they do produce some very coherent results, because they allow us to navigate a latent space that has been made very complex through training it through the corpus of the internet. So that, I think, is back to the perfect storm. We have large language models based upon data and the algorithms and the hardware that allow us to build these coherent kinds of things. But again, we have to be careful. Gary Marcus and I have been voracious and consistent critics of Sam and others.
Okay, I'm gonna round off here, and hope you comment. Write what you think. If you think I'm off the chart, maniac, sure, shoot. And thanks for listening.